Okay, welcome to our first video on matrix algebra. This video will cover some definitions as well as basic operations in matrix algebra. So to start off with, what is a matrix? We'll define a matrix to essentially be an array of values. So here's an example of a simple matrix, 3, 2, 5, 8. This is an example of a 2 by 2 matrix with 2 rows and 2 columns. But you can have much larger matrices. And in practice, sometimes you're dealing with thousands of rows and thousands of columns. But for all of our examples, we'll keep our matrices small because we can get the idea without having to deal with many rows. But so that's an example of a matrix. Here's maybe another example of a matrix. 2, 0, 1, 1. I'll use capital letters to denote matrices, just so that it's kind of clear what's a matrix and what's not. Some special matrices are when we've got either skinny, tall matrices or short, wide matrices, and those are called vectors. We can have row vectors, such as if we just take the first row of the matrix up there, we get a row vector 3, 2. And I'll denote any row vectors with a little t above them. And so let's maybe call this xt. I'll also give my vectors a little arrow. This kind of comes from the practice of vectors sort of being arrows or pointing in space. And so a little t will denote that it's a row vector, and I'll explain what that t is in just a bit. But we can also have column vectors, which are tall, skinny vectors. And so, for example, I can grab the first column of the B matrix, and there's an example of a column vector. Okay, anything that with just one row is a row vector, anything with just one column is a column vector. Okay, why are we interested in matrices? Well, essentially, they're a very compact way to kind of keep track of lots and lots of equations simultaneously. So the main application that we'll be using of matrices are what are called linear systems. So let's start off and let's talk about a linear system of equations. And maybe we'll start off with a specific example. And so maybe this is going to be 3 times our first variable. We'll maybe call our first variable x1 plus 2 times our second variable. We'll call that with x with a subscript 2. And maybe the sum of these two terms equals 4 and 5x1 plus 8x2 equals 6. So we've got 2 equations and 2 unknowns. And we'll often see this where we've got a linear system, linear meaning that we've got constants times variables plus constants times variables plus potentially more constants times more variables. But we don't have any fancy functions like sine or cosine, no squaring or exponents, none of that, but we just have constants times variables. So this is an example of a system of equations, and we can write this in kind of what I'd maybe call this as system form here, as a collection of equations. But we can also write this same system in what's called matrix form. And so transferring it into matrix form, we look at the left side of this, these pairs of equations, and we extract the coefficients. So 3, 2, 5, 8. And then that matrix there is then being multiplied by x1, x2. And we'll explain a little bit later just how matrix multiplication works. But that matrix vector multiplication is then equal to the right-hand side. So 4, 6. This gives us another way of writing the same equation. And then we can give names to, for example, our matrix. We'll go ahead and call that matrix. It's the same matrix as A up here, so we'll call that A. This vector here, we'll go ahead and we'll call that just the x vector. And then we'll call this column vector here We'll call that the B vector. And so we can say that the A matrix times the X vector equals B. And if A is a matrix with these coefficients, if I end up with a different matrix of coefficients, this kind of gives me a compact way of writing whatever matrix of coefficients I have. Here, my X vector is my vector of my unknowns, okay, my variables that I don't know the value of yet. And then in this case, the B vector on the right-hand side is a vector of known quantities on the right-hand side. So this would be sort of what I'd call matrix vector form or a matrix system. And then oftentimes what we'll do is we'll sort of take this same system here and write it in one other form called augmented form. And here we'll just essentially omit the vector of unknowns. And we'll smash the right-hand side into the system, right? And we'll essentially treat it as one matrix. And this ends up being a very convenient way of dealing with this. And then I'll usually label my columns as this being X1, this being X2, and this being my right-hand side B. Okay, and we can see that 3 and 5 were both the coefficients of X1 over here, and 2 and 8 were both the coefficients of X2 over here, and then 4 and 6 were each of the respective right-hand sides. And so this here is called augmented form. This up here, I'd call this matrix form. And over here, this I'd call sort of a system of equations form. Okay, so this is the main place that we'll be using matrices as part of a system of equations. Most of our system of equations will come from linear programming. We'll have a linear system that we'll be dealing with, and we'll be manipulating that system. So this is maybe a specific example of a linear system of equations, but we can write these in general. And so let's maybe write out a general equation or system. And so maybe my coefficients, instead of knowing their values as 3, 2, and 5, and 8, it might look like A11 times X1 plus A12 X2 equals B1. And then A21 X1 plus A22 X2 equals B2. Okay, in this setup, the A's represent all the coefficients. And now instead of specifying specific coefficients, I've just left them as values to be filled in later. And maybe I'll have those stored in an Excel spreadsheet, and my program will sort of read in what are those coefficients and put them in just in time to solve the system. Okay, so there's my system form. And then I could think of this as being an A matrix, where the A matrix is formed from the coefficients. So A11, A12, A21, A22. An X vector with my two variables in it. And then my right-hand side vector that I'll denote B. And these are usually known quantities here as well for the B vector. So usually the A's and B's are known, but the X's are unknown. Okay, and so I can write this system in matrix form as AX equals B. I can also write it in augmented form of sort of just taking that A matrix and then drawing a vertical line to separate it from the right-hand side B vector. I'll maybe write one other equivalent way of writing this system, which is summation format. And so if I think about what's going on here, I'm taking an A times an X plus an A times an X, and that's equal to a B, and then I repeat the process here. And so I can use some indexes, and maybe I'll have I as my first index that will tell me which row I'm in. So this is, notice the first index of both these A's is both 1 here, and then the B has an index of 1. And in this row, the first index of both the A's is 2, and the index of the B is 2. And so in summation notation, I can think of a generic row as being AI1 x1 plus AI2 x2 equals BI. Okay, for a generic row, maybe my ith row looks like that. And then if I look at this, now the indexes here of the second index of the A matches with the index of the X. Same here. The second index of the A matches with the index of the X. And so I can then turn this into summation notation. This capital sigma that looks like a zigzag means add up all the terms that look like this. And so I'm going to replace this 1 and this 2 with an index j that's going to start with 1 and go to 2 of aij xj. And that's going to be equal to bi. Okay, and I kind of left this as the generic ith row. Then I can say for all I equals 1, 2. Okay, and this here ends up being summation notation. A little bit overkill when you only have 2 rows and 2 variables, but in practice, we'll generally have lots of rows and lots of variables, and then this ends up being a very compact notation that is essentially equivalent to this matrix vector notation. So maybe the beauty of the matrix vector notation is that it implies this summation notation without actually having to write it all out. So that's summation notation. Let's talk a little bit about operations and some operations that we can do on matrices. So let's first, the first operation that you might want to do, you got 2 things. You might want to be able to add them together. And so let's take our matrix of 3, 2, 5, 8. And let's add it to our other matrix of 2, 0, 1, 1. And addition works exactly the way you'd like it to, where you just add corresponding entries. So this first entry, I'm going to do 3 plus the 2, because I'll take the 3 from here and the 2 from here, and I'll add them together. And I'll get 2 plus 0, taking this entry and this entry. So I did take corresponding top right corners. Bottom left corners will give me 5 plus 1. Bottom right corners will give me 8 plus 1. And then I can go ahead and do the arithmetic, and I'll get 5, 2, 6, 9. Okay. Matrix addition is nice. Subtraction works the same way. Where I would just subtract corresponding entries. And so that will give me 3 minus 2 is 1, 2 minus 0 is 2, 5 minus 1 is 4, and 8 minus 1 is 7. Okay, so addition, subtraction work exactly as you'd like to. The tricky operation when you're dealing with matrices is multiplication. Okay, matrix multiplication is not element by element in the same way that addition and subtraction are. Instead, you take rows of the first matrix and multiply them by columns of the second matrix. So the easiest way to explain is maybe to just show you. And so if we're taking the matrix 3, 2, 5, 8, and we're multiplying it by the matrix 2, 0, 1, 1, the trick is we want to take the first row and multiply it by the first column. So you sort of think of taking rows multiplying by columns. And so let's take this first row and we'll multiply it by this column. And what do I mean by multiplying a row by a column? Well, I'll take the first entries in this row, multiply it by the first entry in the column, and then I'll multiply the second entry by the second entry and then add them up. And so, and the output is going to go into the first cell here. So 3 times this 3 times this 2 will give a, I'll write as 3 times 2, and then I'll do this 2 times this 1. Okay. Now let's do that same row times now the next column over. Okay, and so that gave us this. Now to get the orange right here, not sure how well the colors are going to show up. I'll take the 3 times the 0. And then the 2 times the 1. Okay, let's go for another color if it will show up. Now we're ready to do the second row, and so we'll do the second row of the first matrix, and we'll multiply it by the first column here. And we'll put it in the second row, first column of the resultant matrix. And so it's going to be 5 times 2 plus 8 times 1. Lastly, we'll take that second row now multiplied by the second column of the second matrix. And it will go into the second row, second column. And so we'll take 5 times 0 plus 8 times 1. Okay. Now let's do the arithmetic. And we should get the matrix 8, 2. This will give me 18 and 8. Okay, so the thing to remember when you're doing matrix multiplication is that you're taking rows from the first matrix and multiplying by columns of the second matrix. Follow-up thing is that if you're going to take rows from the first matrix and multiplying by columns of the second matrix, is that the length of your rows, which is the number of columns in your first matrix, has to be equal to the length of the columns in the second matrix for this to work. And so usually when we're labeling the size of a matrix, we'll call this matrix maybe it having M1 number of rows and maybe N1 columns, and this one having maybe M2 rows and N2 columns. Then we'd call this first matrix as being an M1 times N1 matrix, and we're multiplying by an M2 by N2 matrix. And for the matrix multiplication to work, these two numbers must be the same. And so this N1 is the number of columns in the first matrix. It's N1. Has to match the number of rows in the second matrix. Okay. Otherwise, it just won't work. Okay, so that's an example of matrix multiplication. And maybe the number one mistake or the number one thing to keep in mind when you're kind of manipulating matrices and sort of moving and doing operations on matrices is that matrix multiplication does not commute, which means you can't swap the order of the matrices and get the same answer. And so let's just actually look at this matrix multiplication in the opposite order. So if we look at, scroll up, let's look at this matrix multiplication in the opposite order. I encourage you, pause the video at this point and try to do that multiplication, okay? You probably, well, you won't get this, right? So the order of matrix multiplication matters, and if you do it in the opposite order, you'll get a different result. Pause, and then I'll reveal in just a second. Okay, and here is the result. If you do the matrix multiplication the other way, you get 6, 4, 8, 10, and you can tell that that is a different result than what we had before. Okay, so that's matrix multiplication. Those are the main operations that we're going to talk about. Notice I've got addition, subtraction, and multiplication. What I don't have is division. There is not a nice concept of division in matrix arithmetic. The closest you can get to division is multiplying by the inverse, and we'll talk about that in just a second. But we need a couple of more vocab words or concepts to deal with. Well, first, let's introduce some very maybe the nicest vectors that we'll ever work with, as well as the nicest matrix that we'll ever work with. So let's first introduce what we'll call the standard basis vectors. Okay, these are the basis vectors. The first one we'll call E1. Maybe give it its arrow up there. The E1 vector has a 1 in the first spot and zeros everywhere else. The second standard basis vector, E2, has a 1 in the second spot and zeros everywhere else. All the way to, let's say we're dealing with vectors of length n. The nth standard basis vector has a 1 in the nth spot or the last spot and zeros everywhere else. Okay. These standard basis vectors are really handy and useful for picking apart our matrices. And so two things you can do is you can multiply by, let's take a matrix and multiply by one of the standard basis vectors. So let's take our now familiar to us matrix 3, 2, 5, 8. And let's multiply by, on the right, by the first standard basis vector. Well, if we take this row now, now we're doing a matrix vector multiplication. Works the same way as a matrix multiplication. We'll take this row, multiply it down by this column. Notice that there's only going to be one column to deal with. So if I take this row and multiply down this column, I take a 3 times a 1, and that will give me a 3 plus a 2 times a 0. That will essentially zero out that 2. And so the result that I'll get is just 3. Now, when I take the second row times this column, I'll get a 5 times the 1, and that will give me 5, plus 8 times 0, and that disappears. So multiplying by the first standard basis vector picks out the first column of the original matrix. So multiplying on the right by the first, I'll denote standard basis vector as SBV, extracts the first column. Okay. What if we want to extract a specific row? To do that, we'll multiply instead of on the right, on the left. Now, when we're multiplying a 2 by 2 matrix on the left, we're going to have to use a row vector and not a column vector. And so let's let's use the second standard basis vector now as a row vector. And let's multiply that by our matrix 3, 2, 5, 8. So I'll multiply this row by the first column, and I'll get 0 times 3 plus 1 times 5, and that will give me 5. And now I take that same row vector, multiply by the second column, and I'll get 0 times 2 plus 1 times 8, and that will give me 8. And so if I multiply by the second standard basis vector as a row vector on the left, it will extract the second row of my matrix. Left. The second SBV sort of as a row vector extracts the second row. Okay, and so that's a pretty useful trick with standard basis vectors. We'll use it as we're manipulating tableaus later on this semester. So keep this one in your back pocket. It's a pretty handy trick when dealing with standard basis vectors. Probably the most useful standard trick with standard basis vectors is when we assemble all the standard basis vectors into what's called the identity matrix. Okay, and so the identity matrix, we essentially assemble all those standard basis vectors together. And so I'll do a 3 by 3 identity matrix where I take the first standard basis vector, then the second standard basis vector, and then the third standard basis vector. And when I'm sort of gluing a bunch of vectors that are column vectors together, I'll write them as E1, E2, E3. And I'll kind of put bars between them to say I'm just essentially squishing those column vectors together to form a matrix here. Okay. And this forms what's called the identity matrix. I'll often maybe write this one as I3, denoting the 3 by 3 identity matrix. And what's so special about the identity matrix? Well, let's go ahead and use it as something that we're multiplying by. So let's actually go back to the 2 by 2 identity matrix and deal with our same A matrix that we've been using throughout this video. And let's multiply on the right by it. So 3, 2, 5, 8. And we'll multiply by the 2 by 2 identity matrix. And when I multiply by that 2 by 2 identity matrix, I'll take the 3 times 2 times the 1, 0. This vector here is essentially going to extract the first column of this. And it's going to end up giving us a 3 here and a 5 here. And then this vector on the right, the second basis vector, is actually going to extract the second column. And so the interesting thing is when you multiply by an identity matrix, it gives you back the same thing that you started with. And the same thing would happen actually if you were to multiply on the right by the identity matrix. And so although I said in general order matters when you're multiplying matrices, when one of those matrices is the identity matrix, it doesn't matter which side the identity you put on, you will get the same matrix out, and you can verify that by doing the multiplication. So identity matrix. times any matrix. And as long as that multiplication is well defined by kind of the rows and columns matching up correctly, equals the same matrix. Okay, or maybe writing that in kind of matrix notation is that I times A equals A, or A times I equals A. So I can multiply on the left or on the right by the identity matrix, and I'll get the same thing back out. So that wraps up this video. Next video, we're going to talk about, well, once we've made these systems of equations, how do we actually solve them? So that'll be up in the next video.